Hello and welcome to another show of Teaching Mathematics. Today we're joined by Jacques. Hello, Jacques.
Hello, Helen.
How are you?
I'm wonderful, thanks. A little bit nervous, but I'm fine.
Oh, you'll do great. And then, of course, we have Dylan behind the buttons. Hello, Dylan.
Hello.
And today we are talking about grade 10 Euclidean Geometry. If you would like to join in the conversation, please do by using the hashtag VTMaths. So that's a V and a T with the word maths straight after it. Okay, well, Jacques, you haven't been with us before, so why don't you tell us a little bit about yourself?
Helen, I lecture at the University of the Witwatersrand, good old Wits. I'm in maths education. My experience in geometry comes quite from some time ago, but I'll give you my recent experience. I think people who read the Mail and Guardian Teacher magazine might have seen my articles in the Teacher magazine. I wrote 6 geometry articles, and I'm very excited about them. So yeah, that's my experience on geometry. And mathematics, I've got, 25, 26 years of experience.
Oh, you don't look old enough to have that much.
Thank you.
Well, thank you, Jacques. Before we go on, we're going to first take a look at something we usually do at the end of the show. And what we usually do at the end of the show is that I'll talk about a book that I'm currently reading. I'm reading it very slowly, maybe 2 pages a week, where it has 49 actionable steps that teachers can do to teach better. And today's actionable step is the 4 M's. The 4 M's are talking about 4 ways or 4 things to consider when you're planning a lesson. So last week we talked about begin at the end, where you plan your lessons, you plan your whole section, and you think about what's happening you want to happen at the end of the section, but you think of it at the beginning, and then you section off the content according to the plan. The 4 M's then talk specifically about each individual lesson, and the 4 M's are manageable, measurable, made first, and most important. Manageable is the content or the skills manageable within the time frame of one lesson. So don't go and say that you're going to teach this big concept, factorizing trinomials, in one lesson. Oh, let's just say factorizing. Don't say you're going to teach factorizing in this lesson. Rather say you're going to teach the difference of 2 squares in this lesson. After that, you say measurable. How do I measure that I've actually taught this? And there's got to be some kind of exit activity. Now, I don't think I've used the best example because it's talking specifically about a skill over there, and it can be anything. It could be a piece of content. It could be a feeling the learner has after doing it, maybe like building confidence within a certain thing. The next point, though, and that's why I'm rushing ahead, because the next point, made first, is the one that I'm really excited about. So often we use our textbooks to define the activities that we're doing in class. Now, this process is saying that we shouldn't use the textbooks to define the activity. We should, or define the manageable content or whatever. We should rather go, this is what we want to do. Let's either find an activity that suits it, or design the activity if we can't find one that's appropriate. So don't use something because it almost fits. Rather use something that fits for the objective you have. You see?
That's very, very important, because
I think so.
Often we can bring in what they call, out there in my field, in the academic field, we call it noise. There's a lot of noise surrounding an activity. And if you bring the wrong activity to the table, you're creating more chaos in the child's head than what you're actually creating refinement, because that's why you're going to choose a particular activity, as you said, to bring across a particular skill. So it's very important. It's a very, very important step.
I think so too. It's wonderful. Then the last thing says most important, and it's basically saying keep the most important thing, which is exactly what you're saying. It's you've got the activity, you're looking at your manageable content, you're looking at how to measure it, and you've got to reflect the whole time. Is all of this keeping in line with the most important thing? And as a teacher, if it's not keeping in line with the most important thing, whose responsibility is it to fix it? It's not the learners, it's the teachers. They've got to go back and reflect on that.
Exactly.
Yes, now Jacques, the reason I put this at the beginning is because I think it ties in really nicely with the Euclidean geometry thing. Because, well, let's take a look at the CAPS document quickly, or the copy and paste version. I did abbreviate it slightly, of what's meant to be done in term 2 in Euclidean geometry grade 10. And in the CAPS document, it's actually 3 points. I've divided it up into 4, and it doesn't say very much, does it? For 3 weeks.
No, it looks very little. I mean, if you look at that, that's supposed to compose 30% of the exam at the end of their year, is their Euclidean geometry.
And all they're doing is revising lines, angles, and triangles, investigating line segments joining midpoints of the sides of the triangle, and then the quadrilaterals.
Exactly, yeah.
So
it's going back to what you said in the opening, is finding not only examples that brings the content that's listed in those 4 points to the classroom, to the table for learning, but it's also finding additional examples that we'll talk about this later on, that creates the relational thinking that's necessary in geometry. And we don't do that often enough in our classes. We think that if a child is good at mathematics or good at algebra, one component of mathematics, that child is necessarily going to be good at trigonometry or at the geometries that are in the curriculum. And that's not necessarily the case.
yes.
Your child has got to be an all-rounder mathematician to be equally good at all 3 of those focal points in maths. And geometry is a total different thinking skill.
It really is.
So for a teacher, it's important to actually go and look for those additional examples that creates the depth that the textbook doesn't necessarily create.
Yes. Yes, Dylan.
Can I just jump in with a quick question? You've just said that all 3 elements, aspects of maths are important. I just want to check something. Is geometry in there in the first place because of the particular kind of thinking skills that it fosters and develops?
I think so, yeah. If you think about the difference between reasoning algebraically and reasoning geometrically, geometry, the type of reasoning you need it's a visual reasoning linked with doing the mental gymnastics in your head. If you do geometry, now this is how some teachers teach it, and I was personally taught this when it didn't work for me. So my second paper I always had 52%, and my first paper was always in the 80s. My teacher told me to, whatever you see that's equal to each other in the diagram, write it down. And you can later on go and physically take that N3 and link it to the N3 here, and link it to another relationship with N3, which you can't do. You can maybe get away in algebra by doing things like that. But in geometry, you can't. In geometry, a lot of what happens is in the mind. You make your connections in your head, and you establish relationships in your head, and then it goes from your head to paper. It's a complex process. It's a very layered process. And it involves language, it involves symbolism. There's a lot more involved in reasoning, I think, geometrically than in algebraic reasoning. And algebraic reasoning has its own complexities. So I agree with you. I would hope that is the purpose of geometry, that it teaches that separate set of skills to our learners. And the teachers must be aware of that. And you cannot teach geometry algebraically. You can use algebra in geometry, but you cannot teach it the same way as what you teach algebra. Yeah.
Now that you're saying that I mean, if I thankfully left the classroom before I had to teach Euclidean geometry because I was petrified of it, and I think a lot of teachers can relate to that, that they're just scared of teaching this complex thinking whatever. But if I were to teach it, I would very definitely approach it in the same way as I would approach teaching algebra. So what you're saying there is that I would be completely wrong.
I would definitely say yes.
Okay, I'm quite happy with being completely wrong. As long as you can show us the right way.
Not 100% wrong, but yeah, it's a different set of skills.
Yes.
And I've seen, being at the university, I see how my student teachers teach geometry, and how that is put against what they see the traditional teachers teach, who's in the school. And it's a total different approach to the teaching of geometry. And I think that is what is important, and that's what we need to discuss here today as well.
So you're saying the more traditional approach, the approach that I was educated in and you were educated in, Dylan, is not necessarily what we should be talking about today. We should be talking about creating this thinking mindset.
Exactly. Doing things a little bit differently that empowers the child to do geometry and not become a little Jacques or a little Helen or a little Dylan.
There's nothing wrong with me. Before this is going to be a good conversation. I'm looking forward to it. But before we get on to it, Dylan, why don't you show us where we can find resources on the content if a teacher is struggling with the content. Here is our new website. It's very exciting. If you would like to go to the mathematics section, you would go to subjects and then scroll down to mathematics. And because we're talking about grade 10 today, you'll see it opens up to grade 10, and we've got term 1 content at the top, and you scroll down to term 2, click on Euclidean Geometry, and it lists all the resources for you immediately. And there they are. So easy to find our resources now. It's fantastic. But I'll put those links up on the website, up on our blog at least. So if anyone does want to revise on their Euclidean geometry knowledge, then they can do that. Although the knowledge that we're going to discuss today isn't really that difficult, is it?
Not at all.
No.
Not at all. What the learners have to know at a grade 10 level is very almost elementary in the bigger picture of geometry.
Yeah.
But it is very important that the skills that we're going to talk about today is developed while the geometry part of it is still easy to cope with.
Yes.
So that's I think our big message will be today, is how do we do things differently to do what Dylan alerted to earlier, to develop that different way of thinking when you think geometrically.
Yes. And you're going to talk specifically about a book called Review of it's Fostering Geometric Habits. Dylan, can you click on that link for us, please? I found a book review on it. And it basically says that from what I can read in that first paragraph, Dylan will have to read it to us in the grey section underneath overview.
Okay, trends in international mathematics and science study have shown that American schools have consistently helped students understand algebraic and statistical concepts, leading to high achievement internationally. Now it's time to do the same for geometry. Mark Driscoll, author of the powerful and popular Fostering Algebraic Thinking, takes up the challenge and leads you to new research-based ways to improve how your students conceptualize and apply geometric ideas.
So basically this man, Mark Driscoll,
yeah.
Yes, has looked into the 4 habits of a geometric thinker. Yeah,
He's
that correctly?
Looked at how they're thinking, and he's created, I think rather the other way around, he's separated them into 4 general habits.
Okay.
That he calls the geometric habits of mind.
Okay.
And it's important for teachers to foster these habits of mind in the context of geometry, clearly, because it focuses on geometry. Shall we start with that conversation?
Let's take a look at that first slide, which lists the 4 habits. And there it is.
It talks about seeking relationships. We'll talk more about that. He talks about his second habit, which is checking the effects of transformations on particular diagrams. Then his third habit that he talks about is generalizing geometric ideas. And finally, balancing exploration with deduction. Now, when Driscoll talks about seeking relationships, Helen, he's talking about relationships that exists within a particular geometric diagram. So you might have quite a few lines. How are those lines related to one another? In the context of what we're looking at quadrilaterals in grade 10. So,
okay.
And we have different type of quadrilaterals. So with opposite sides that are parallel, what type of figure does that create? What relationships does it create within the diagram itself? So in other words, if there are parallel, let me draw this. If there are 2 lines that are parallel to one another, let's just do any 2 lines. We've got those 2 that are parallel. We can create quite a few geometric diagrams with 2 lines that are parallel. One of them will be to create the parallelogram this way. Now I'm saying line here, it's actually a line segment. Or we can, if we drew this line this way, we created the trapezoid. If we draw the line perpendicular to the line, the other line, both sides perpendicular, we've created a rectangle.
Yes.
So that creates various relationships within the diagram, between the angles, between the sides. You can also have those relationships existing between separate different concepts.
Okay.
So for that you might have two separate quadrilaterals, a diagram of a rhombus and a diagram of a square, and relate the two.
Okay.
How are these two things the same? How are they different?
Is he saying that when we start a section like this, we should start with a group of, in this case, quadrilaterals, and we should just be comparing them to find relationships between the two?
I think the most important thing to start, before we even go there, Helen, is to actually find what they call a working definition. So that's a definition that's not refined to actually define a quadrilateral. It's a definition that we're working on in class, and this is what's so beautiful about geometry and about mathematics in that way, that you can chop away at your working definition and seeing, okay, hang on, here my definition is falling apart.
Okay.
What do I need to refine in my definition? What do I need to add, and what do I need to take away to find a final definition that works for quadrilateral? And it's nice to walk that journey with learners. There's a whole theory about realistic maths education, the way the Dutch educate. There was a man, Pierre van Hille, which I think teachers most probably would have come across.
Van Hille's something.
Levels of geometric
yes,
thinking.
that's it.
Now, I don't even want to go to Van Hille today because it is such an exciting, and we can do a separate program on that.
Oh, good.
But a lot of what we're going to say today, if people are familiar with Van Hille, they will see that it actually supports what Van Hille has said.
Okay.
So the idea of defining the tool that you're working with and refining that definition. We're going to talk later on about creating limiting constructions through our definition. And I think in that way, we sort of avoid the issue of limiting constructions. And by that we mean defining something, and when we move on to a more complex diagram, that definition falls apart. It doesn't work anymore.
Okay.
So starting off with working with examples, like you're saying, of various different quadrilaterals, and maybe then saying, stop, let's define this object that we've been looking at and break it up.
And would you define the quadrilateral as a whole, or would you define the individual quadrilaterals at that stage?
So now this is where Driscoll is when he says about seeking relationships, his first habit, you would want to do both.
Okay.
You would want to relate, why is that figure a quadrilateral, and why is that figure also a quadrilateral, and it looks completely different. Let's put two drawings on here. The basic quadrilateral shape that, I'm going to try and draw it so that it doesn't look like a particular quadrilateral. And then this type of idea. There we've got the word quad, which means four, and lateral, which refers to the sides of the figure. So if we deconstruct the word into those two words to create a definition of the object we're going to work with, at this point it will be a four-sided figure.
Yes.
Figure that has four sides. It doesn't even come to the idea that this figure has been has to be a closed figure. So in other words, that this belongs to a polygon family.
Yes.
So if that was the case there, that would definitely not be a quadrilateral because the figure isn't closed. So that might come up in conversation in a class when you're busy working on your working definition of what a quadrilateral is. But ma'am, here's four sides. I've got four pencils or four pens form a quadrilateral. Can I put them anywhere, or do they have to meet? So that brings out then the idea of the 4 vertices, and that this figure actually has to be a closed figure to qualify to be called a quadrilateral eventually. Now that naturally then moves into the issue of a polygon. So it's a complex thing. And I mean, I said to you in the beginning of the show, or before we started the show, that if you go into the mathematical websites, they say it's a contestable definition that they give for polygon. Some agree, some don't.
Okay.
And I think it's necessary for learners to go through that process of creating the definition for the object that we're going to work with.
Very small question, perhaps. Would you suggest that in working with this definition and refining it over time, that you're actually encouraging your learners to break it, to see where the working definition breaks down, and to think about why it's breaking down? Is that sort of the approach?
It will be if you move from a particular class of figures. I'm now thinking in terms of the issue of, let's say, a diagonal. That a triangle doesn't have diagonals. The first figure that the learner comes across as having diagonals is the quadrilateral. So what we usually then will say to learners is that this diagonal is a line that, sorry, my line is not that straight, that runs from the one vertex to the opposite, I hope you can see that, to the opposite vertex C, if this is a quadrilateral ABCD. And that's okay if one works with quadrilaterals.
Yes.
But the moment you go to a pentagon, there's an extra vertex, so there's 5 vertices.
And when do you draw it? Draw it then.
Exactly. There's this angle. If I put another vertex in here quickly, and let's just call it E, there's this vertex, but opposite to it, there's 2 other vertices. So does it then make sense to define a diagonal as a line joining the opposite angles of a quadrilateral? Yes, it is. But we cannot define the diagonal like that. We can define a diagonal in a quadrilateral like that, but not in the pentagon. So that's I think, a nice example of where the definition comes apart, of saying that a diagonal is a line that joins opposite vertices with one another, or joins a vertex with its opposite vertex. Because now all of a sudden in the pentagon, that's no longer the case. So we'll refine the definition to say, but hang on, let's see how these vertices are lying in relation to this vertex, and then bring in the idea that it's a non-adjacent vertex. So that then a diagonal becomes a line going from one vertex to every non-adjacent vertex.
Okay.
And then if you reverse right back to the triangle, that's why a triangle doesn't have diagonals, because each vertex is adjacent to one another. So it's these little things in geometry that I think, and we tend to forget about the importance of this. I say to my students always, the devil is in the detail. So that's where things come apart, is the moment you start digging in the detail of things that you see that, hang on, my definition is a bit shaky here.
It's a good skill to teach students. Okay, shall we move on to, are there any questions that you need to be asking while you're doing this, seeking the relationships?
Driscoll suggests quite a few which he talks about, which are nice. I'm just paging to the reference that I need here. He says when you talk about the first habit and you're talking about relations, you need to ask yourself, when you're looking within a figure and between figures, how things are the same and how things are different, and what it is that makes it the same and what it is that makes it different. So what do I do to a square, for instance, to turn it into a rhombus?
Yes.
Because they share the property that the diagonals intersect at a right angle, but they also share the properties that all 4 opposite and adjacent sides, all 4 the sides in the figure are indeed equal. So how does that definition gets chopped and changed to become the rhombus? we need to think about what it is that's actually changing. The sides are still parallel, they're still equal to each other, but we often refer to, and I've often done this as well when I taught, still taught at school level, to explain a rhombus and its relationship to a square, I just need to take a square and press it over, because then it becomes the idea, the issue of a parallelogram sort of takes over, where your opposite angles are equal, the sides are still parallel, they're still equal, the diagonals are still perpendicular. So how across the two figures did things change, and why did they change? So it's one of the questions that Driscoll says that you need to ask when you look at, when you foster the relationship seeking in your geometry class. Yeah.
Okay, so by asking those sorts of questions, you are fostering that thinking that he's talking about.
You're forcing a child to actually think relationally, not just to think about the action of squeezing, but which relationships were violated, if we can call it that, in the square to create the rhombus. Or what do you need to change in a rhombus to turn it back into a square? How does a square turn into a rectangle?
You know, this sounds a lot like something we could apply to the 4 M's. We say that kind of those kinds of relationships we want to see a learner be able to define by the end of the lesson. And then you could measure it. I don't know, how would you measure it? Would they write it down? Would they draw a mind map? Would they?
That's a good idea, is to actually write those relationships down. A lot of textbooks, Helen, have that table at the end of the quadrilateral section, where they have a square and they've got all the properties that one can look at, and then you tick off which properties belong to the square and which belongs to the rectangle. But we tend to only look at those tables horizontally.
Yes.
So the square has a right angle, it has opposite angles sides parallel, opposite sides equal, diagonals intersecting at a right angle, diagonals equal in length, diagonals bisecting. I mean, we can carry on. The diagonals in relationship to the area, but we don't look across vertically that often. Sometimes we do, but more than often we don't look at that table vertically, so that if we see, okay, angles are 90 degrees, there's 90-degree angles in the square, there's 90-degree angles in the rhombus, there's in the parallel, in the rectangle, etc., etc.
It sounds like it could actually turn into quite an interesting activity.
I think you can, and you can then also say, for instance, can a quadrilateral, sorry I interrupted you.
No, please. I'm having a thought process, so
I
you're
can
giving
see
me
your
time.
eyes are
Yes.
You can actually then ask, can diagonals in a quadrilateral that are bisected ever have the quadrilateral opposite, I'm just using a wild card here, opposite sides equal, for instance. We look at the properties, what I'm trying to say is we look at the properties of the angles, the properties of the sides, the properties of the area, all as separate things that we need to look at, but we never mix them up. So if there's diagonals that are intersecting at a right angle, what are my possibilities of shapes that I can have?
Yes. Okay, so I've thought of an activity, and you must tell me, because I've just thought of it now, so you must tell me if it's silly. Okay, so divide them up into groups of, let's say, 6, and they're being grade 10s. They like doing group stuff, and get them to act out how a square can change to, let's say, a parallelogram by only changing one thing at a time with their bodies. So the square could be 4 children lying perpendicular to each other, and then change it to, they could change it to a rectangle next by adding 2 extra students, and then squeeze it, changing one thing at a time, or something like that. But then maybe analyzing the changes that happen to the diagonals at the same time as doing all of that. Yeah, I don't know. You see, the maths teacher in me is going, but they aren't writing it down. They need to be writing it down and doing it with a ruler. And
you know what's a very powerful tool, Helen? And I'm not, the tool of construction. So having learners learn Euclidean geometry by using a straight edge and a compass. So there's no ruler, there is absolutely no protractor, nothing on that table. There's a straight edge without markings on it.
Yes.
And there is a compass. And to get them to start constructing various quadrilaterals. It's a way of enforcing the property, because the difference between drawing a square and constructing a square, and this is where the textbook, I think, fails. A few textbooks, quite frankly, is it says, there's your protractor, construct a 30-degree angle. That's not constructing, that is drawing.
Yes.
You need to put your protractor on the precise point and then tick off where the 30 is, and then draw in the 30. There's no construction involved there. Whereas if I ask you to construct a 30-degree angle, you might think, okay, goodness me, I've got the straight edge, I've got the compass, I know how to construct an equilateral triangle where all the angles are 60, and then I go and bisect my one angle, all processes that are relational. And by bisecting the one angle I've created and constructed the 30 degrees. So if you go and you're in a class where you want learners to learn about the square, for instance, I would say that would be a brilliant activity, because now they need to think relationally. What is it that makes the square the square? There's perpendicularity, there's parallel, there's equidistance, all of these that are very powerful geometric tools, which, if we draw it, goes by the wayside. They never experience how these different concepts in a geometric figure needs to be put together, almost like a puzzle, to make the picture of a square. So that's another way to sort of get them to move away from the visual and actually think about the relationship within these diagrams. Pretty much is what you said now, with them forming their bodies in such a way that they create a figure that where all four the sides are equal to one another. And how do they change that to create another figure where there's certain relationships that are maintained and others that are changed? And what is it that's changing?
Yes.
That's his first habit, the seeking of relationships. What is it that makes a square a rectangle, but a rectangle not a square?
Yes. Okay, we need to move on to habit 2, unless you want to say anything more about habit 1. Okay, and habit 2 was, you'll have to remind me.
I will get to it. Oh,
checking effects of transformations. Thank you, Dylan.
Yeah, there we go. So, before we go on there's one thing that I just want to emphasize, and that's the mixing up of these properties. If we look at a quadrilateral, what are the properties that we're going to work with, or the geometric objects? We're going to work with 4 sides. We're going to work with 4 angles. There's 2 diagonals, and something that we almost always forget to mention, but it's a powerful tool to use, especially if we want children to construct their own proofs based on the conjectures and stuff that they've made.
Which is stipulated in the CAPS document.
Exactly.
Yes.
Is that a quadrilateral can always be divided into 2 triangles or 4 triangles by its diagonals, depending on whether you use both.
Yes.
But the issue that there's triangles in the quadrilateral is a very powerful tool. And we'll look at an activity later on where teachers can actually link the activity that comes later on in the year when they work with the midpoint theorem to the concepts of the quadrilateral. I love that activity. We'll talk about that.
I look forward to it.
And then there's another property that we don't often refer to, and that's the property of the area of a quadrilateral.
Yes.
Now that breaks down to the areas of the triangles that are formed in the quadrilateral.
And that's not often taught that way.
Exactly.
You're just given a list.
I mean, I found myself today out of need, I didn't even think about it, to go and look for the property, the area of a trapezium. And I thought to myself, my goodness, if my students could see me now, what would they say? Okay, let's move to habit 2. It says that checking the effects of transformation. So this is... if we got the slide up there,
Yes.
he talks about analyzing which attributes of a figure remains the same and which changes when a figure is transformed in some way. So that transformation could be a transformation in the orientation of the figure. It could be rotated. It could be shifted. This is where Van Hille is very big.
Yes.
Presenting learners with other ways of orientation. I'm not saying that clearly. Let me draw it for you. If we teach, for instance, triangles, Van Hille maintains, and this is quite true, I've seen it happen again and again, and I myself. If we talk about a triangle, that's how we as teachers orientate the triangle on the board.
Yes,
Van
always.
Hille says then a child doesn't see that as a triangle. Now, clearly at high school level, this is totally developed already, and a child will know that the two are definitely both representing triangles. So it's this different orientation. Don't always, if you talk about a quadrilateral on the board, always draw a quadrilateral that lies like this. If you're talking about a rectangle, draw different variations. Place it balancing on that point, or represent it in a long way where your short side is the base and the height is your longer side. So it's important for learners to see that nothing changed, it's still a rectangle, and to get used to that process. So it talks about attributes of the figure that we can change is its orientation, its location, its area, perimeter, and volume, side lengths, the ratio of the side lengths, and the angles in the shape itself, in the quadrilateral. So let's bring it more closer to what we're looking at in the grade 10 curriculum. If we're talking about opposite angles in a quadrilateral being equal, let the child draw for you on the board all the figures that he can generate that are quadrilaterals where opposite angles are equal. And I bet you, Helen, that this will be the first one that they draw, is either the square or the rectangle, because they're they're going to be so used to working with that as their quadrilateral.
Yes.
Later on in their grade 11 year, they need to work with the fact that the quadrilateral is now concyclic. Then different other relationships comes into play. But if we don't teach them now to think about those relationships, and we just present them with these neatly packaged problems that we use in class, we don't afford them the opportunity to think critically about the problem that they're busy doing and the relationships that they use to answer the question.
So if I understand you correctly, habit 1 was analyzing the relationships between the quadrilaterals. Habit 2 is taking a particular quadrilateral and turning it every which way and making it every which size you can to reinforce that this is always going to be a rectangle, or this will always be a kite. It will always have the properties of a kite. Doesn't matter if it's upside down or...
And working with those properties in different ways. So you might, if you want to talk about the kite at one level, work with only the side relationships, and at a different level work with opposite angles. Or at another level, what the diagonal does to those angles, and then move away from the kite. And I mean, as teachers, we know that the long diagonal in a kite bisects the two opposite angles that are not necessarily equal to each other. But now, what if those two angles are equal? What changed? So that's a shape that you might think of as a shrinking shape to get the two angles the same. So the transformation is we sort of squashing it down, shrinking the shape to become what should we call it? A rhombus, help me. Where the opposite angles are also bisected by the diagonal, or a square. So the issue is here, a diagonal is bisecting two opposite angles. Now, instead of just staying in the shape, which you said, staying in the shape of a kite, we've established it now quite soundly in the kite. Let's see how can we change a kite to become one of the other figures and is that relationship with the diagonals and the opposite angles, is it violated, or is it still the same relationship? Did it stay the same? If that is what stayed the same, then what changed?
Is violated the correct word to use? Or is it something that you've coined? I'm sorry.
I often talk of properties being preserved.
Yes.
Or properties being violated.
Okay.
And it is quite my mental image all of a sudden is now very violent. Take a hammer and hit it flat.
It does make sense, and maybe it brings across the point better than saying, how have we changed this? It's because violated implies that it's been changed in a way that's irreparable.
Exactly, yeah.
So I think it makes sense to use it. I just wondered if it was the correct academic word. And
we can say disrupted, I suppose. If we disrupt the property, how does the shape change?
Yes.
Yeah.
Terminology. We could talk for hours, but let's move on. Is there anything else we need to discuss with Habit 2, or have we summarized it quite?
I think we need to, and this is a big thing as well on certain of the maths websites that I often go to if I'm not so sure, and one of them is the Wolfram World of Mathematics. I think it's a brilliant website for teachers to go to, because there you have your refined definition. It's pretty much the Wikipedia of the mathematical world out there, the purest mathematical definition you'll find on the Wolfram website. They call it Math World or Wolfram World of Mathematics.
Dylan has actually pulled it up for us.
Oh, there we go, Dylan. Brilliant. Now, if you type in there quadrilateral, even polygon, type in polygon, then you'll see that they say to you that the issue of a polygon has not been resolved. I think it's the first or second one, Dylan. You just have to see the one that will be accessible to. Yeah, there we go. Where they say that the idea of the definition in some textbooks says that if the polygon, the sides cross over, that it's not a polygon. So in terms of defining a quadrilateral, that is a crossed quadrilateral. So if you want to use a polygon to talk about a quadrilateral, the two are not talking to each other. So one needs to be very aware of that.
Okay.
Now, there's something about taking a shape that is irregular and turning it into a regular shape as well, which Habit 2 does talks about. It's the transformation that we use. So talking about a regular figure in a triangle, it's okay to say a regular triangle is an equilateral triangle. A regular quadrilateral is also equilateral, but there are certain of the properties that's different between the square and the rhombus, but both have the four sides equal to one another. So immediately there the definition comes apart. If we go to a pentagon, it explains it quite nicely, because you can have dents in that pentagon. The angles are not necessarily equal, whereas for the triangle they were. Whereas for the square they were, but for the rhombus they weren't. And there's a difference of all four angles are also not equal.
Okay, so you're saying that a regular polygon is just a polygon that has the same length sides, and the angles it doesn't actually matter.
It has to have the angles. No, I'm saying the opposite. The angles also have to be the same. And that is the perfect example there is the difference between the square and the rhombus.
So you're saying the definition doesn't really match what...
Yeah, it doesn't make provision for that refinement of the angles and the sides create the general figure.
Okay.
Now, I found a beautiful description of that on the Wolfram, which I put onto the slide. Slide that's... No, the previous one, Dylan. That one. Where that regular square, the square is placed within concentric circles. So what they argue on the Wolfram website is that if a figure is a regular figure, then that regularity, like the square there, we can inscribe it and we can circumscribe it from the same center. And that is a relationship that is very highly complex. You can imagine if you got the pen, now right next to it I put the What if we only looked at the sides, what would define a regular pentagon? But if that pentagon isn't regular, it's only regular in terms of its sides, but the angles aren't the same.
Yeah.
Okay, so it's that whole issue of how do I then, this is what habit 2 says, how do I then talk about that regularity in the figure itself? Now, habit 2 also, to talk about quadrilaterals, sorry, this is actually what I want to say. We can talk about the regular quadrilateral versus the irregular. We can talk about the concave versus the convex. We can talk about symmetry. Learners learn about symmetry when they're in primary school.
Yeah.
And all of a sudden, we've had transformation geometry come in. Symmetry became very important. In the function stuff, symmetry is important. I saw your program with Craig.
Yes.
And you guys spoke about that. There's symmetry in functions. There's just as much symmetry in geometric shapes, but we don't use it. We don't necessarily talk about it. So there's another relational issue. Why does the square have four lines of symmetry across its diagonals and across its side bisectors, where the rectangle doesn't?
Yes.
So what was, to use my language again, what was violated from the square to the rectangle in terms of the symmetry? That conversation, I feel, must happen in class for us to work with these shapes and work with them effectively in a way that sort of creates a relational view again.
Yes.
I mean, it's what is the diagonal there for other than bisecting the area, cutting the area of the quadrilateral, or not necessarily bisecting, but just cutting it into two lines? We never go beyond that.
Now, it sounds like you're saying, in comparison to the traditional line of teaching, where I was given a list of quadrilaterals and I had to learn all the properties, and the next lesson we had a test. Rather than doing that kind of teaching, it should be a week or 2 weeks long of exploring all of these and exploring the lines of symmetry versus the diagonals and all of those things. Is that what you're saying?
I'm saying, yes, exactly. Well, exactly that. The diagonal is a line of symmetry, and we never use it. So we don't use that property of what a diagonal does in a shape. It's not always a line of symmetry.
Yes, I'm thinking of your pentagons now.
Exactly, yeah. So learners have to see in which figures do the diagonals form part of the symmetry. Later on, I will never forget this, years ago, there was in the analytical geometry section, there was a line passing through the centroid. That was a two-mark question, passing through the centroid of a triangle, and they were asking, what does it do to the area of the triangle? Now, the answer is that the area is bisected. It goes through the center point.
Yes.
But now, that's a procedural way. I can tell you that, let's say the area is bisected. For you to understand that the area is bisected, you need to understand what relationship does the centroid have and align through the centroid with the rest of the triangle that you're working with.
Yes.
And that's a complex relationship for a child at grade 10 to start understanding. But as we, Helen, I'm maintaining, as we said in the beginning, there's 4 points that learners need to know in grade 10. So I think we actually need to lift the bar in grade 10 to help these learners cope with what's coming in grade 11.
So get them into the right frame of mind, the right thinking, so that when they get to grade 11 with all of the complicated theorems and things like that, they're in that mindset already.
Get them in habits of mind, exactly what Driscoll is saying.
Okay, so devil's advocate here, we're teaching this at the end of term 2, and yes, we do a little bit more in term 3, but grade 11, Euclidean geometry is a year away.
Yes.
Are they going to maintain that line of thinking?
Well, I think if we enforce it good enough and deep enough in grade 10, and we foster these habits, it becomes a way of doing geometry. It's not just about, now I've got a new theorem, this is what the theorem looks like in a picture, so I need to look for this picture in a diagram that has 200 other lines. they don't think about the picture, they think about how this line is related to that line.
Yes.
And what was the consequence of that happening. Now, again, the figures are so basic in grade 10. I mean, we can open any textbook. It's got parallel lines in it, and it's quadrilaterals. It's a very, very limited scope in grade 10.
For that reason, I think a lot of grade 10 teachers would be tempted to cut the section down to 1 week and spend an extra 2 weeks on something that their students are
battling with, yeah. And that is exactly what we don't want them to do.
It sounds that way.
Yeah.
Shall we go on to habit number 3, which is generalizing geometric ideas?
Now, this is where my... I told you the lovely problem that I want to look at. And this is let me draw this.
It says on the slide, wanting to understand the always and the every related to geometric concepts and procedures.
Yeah.
Yes.
So if we look at any quadrilateral, for instance, I want to draw it as skew as I can. There. That is any quadrilateral. There's nothing that looks regular there. And we take the midpoints of each particular side. So now this is a lovely problem that you can do with your grade 10s. And you join those midpoints. Now, I'm sitting at an angle, so I hope, Dylan, you'll be able to tell me. That looks like a parallelogram in the middle.
From my angle, it does as well.
It looks almost like something more than a parallelogram.
A rhombus.
Could be.
Yeah. Okay. So, folks, then now we're totally on the visual level. We've taken these sides and we have bisected them and we've joined the midpoints with one another. Now, immediately, if you stand back and you ask your learners, what shape do you see? Parallelogram, rhombus. The issue being then that these sides appear to be parallel to one another. Now, what they learn in the third term will help them deal with this. That is almost why I think the two are the wrong way around, that the triangle should have come before the quadrilateral. But that's just my own preference. So the next question, according to habit 3, would be, okay, learners, what do you think? Do you think it will always be a parallelogram? And then to maybe draw a kite on the slide. Now, I think I've got that on the next slide.
Yes, we've got it up on screen.
There we go. There's our 4 different quadrilaterals, and we can see inside each one of those, I've joined the midpoints of each side. And it seems to be true that there is definitely a parallelogram of some sorts if I join the midpoints of the sides. Now we move to habit 3. Is this always going to be the case? And you want your learners to answer that question for you. So you leave them. This is the type of activity that gets them to think about the relationships that they have learned. Now, one of the relationships, they're going to want to prove that this is a parallelogram. So they most probably going to start looking at, is that side equal to this side? Or are those two sides equal to one another? Because if they are, that's one of the properties I've learned about. Or the opposite angles, whichever way they want to think about it. But that will keep them busy for quite some time.
It opens a lot of doors to thinking.
Exactly. Now, if you look at it, I'm going to cut it short because I think our time is running out on us. This is where their midpoint theorem comes in beautifully, because if you just draw one diagonal in there, you've got a line running from one side to the opposite side, forming the triangle.
Yes.
Running from one midpoint to another midpoint. So immediately it makes those two parallel.
Yes.
But if we move into the bottom half of the shape, again it's a line running from one midpoint of one side of a triangle to the midpoint of the other side of this bigger triangle. So that diagonal is also parallel to this side.
Yes.
And there we have two of the sides parallel. We don't have them equal yet.
Yes.
But that's a conversation we can now have using our theorem, our midpoint theorem, that this side is half the length of that red line.
Yes.
And that one is half this length. So the property I'm using in this case would be parallel and equal to prove that that's parallel.
Mm.
Or if they just wanted to prove parallel and parallel, they would put the other diagonal in and repeat their argument. So can you see how beautifully they then use the properties?
It would
to
actually
argue
make
with.
a really good investigation that they could do on their own and then argue the points themselves.
Exactly, yeah. Now, let's say, for instance, I want to move to habit 4 because I think this is a nice example of what habit 4 is saying. Habit 4 is saying balancing exploration with deduction. Now, they're saying this is an iterative and cumulative process.
You need to explain those two words to me,
So
please.
iterative means
Yes.
you repeat the process over and over and over. And every
Okay.
time you repeat the process, you refine something.
Okay.
Now, that is the analogy of the definition, chopping
Yes.
away at the working definition. Okay, let's revisit our definition. Our definition didn't deal with this issue, so let's bring that issue into the definition. Iterative, and what the second word I used there was?
Cumulative.
Cumulative, yeah. Cumulative meaning every time this whole process accumulates to a proper definition.
Yes.
So I repeat and repeat and repeat over and over and over, and that builds up to something that's going to become a mathematical definition in the end.
Yes.
So if we think about that habit in the relationship to this problem, your learners would have wanted, let's just say, Helen, wanted to use the fact that they want to prove that this angle and this angle are equal and that those two angles are equal, and therefore it would be a parallelogram. Or they might have wanted to start drawing diagonals within the parallelogram. Now you know that that's going to lead to nowhere, because the relationship is with this red diagonal.
Yes.
That brings in the pathway to answering this question. There might be others as well. So you leave them enough to see that, yes, those properties were true, but to argue the point that I need to argue here, it's not leading to anything. It's not leading to something that I can use and relate it to the complete figure.
Yes.
It's only related to the inside figure. So what the habit is basically saying is, yes, explore, 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 and it's your duty as a teacher to know when to rein in and when to focus a learner, when things are needed to be focused. So one learner might have, for instance, in your class say, oh, I want to work with that. Now you know that's going towards the answer. So
Yes.
you would pay more attention as a teacher and say, listen, class, Helen has just suggested we draw a diagonal. Now, can you see that diagonal transverses the parallelogram? It cuts right through it. How do you think she's going to use the parallelogram? Oh, sorry, use that red diagonal
Yes.
and relate it to the parallelogram. So it's a very interesting journey to walk with learners, but it's a necessary one. And it often means that teachers need to let go.
Very
as-
difficult for a maths teacher to do.
Exactly.
Yes.
We're not the only, let go of, you're not the only one with the knowledge. You have the knowledge and you want them to get there.
Yes.
Instead of being, demonstrating it to them, because that's when the relational issue goes missing.
It almost feels like our textbooks and all of our current resources are letting us down, that they're teaching things in a too formulaic way, that it feels like we need some kind of investigation that lasts 3 weeks, that takes them to this point where they discover it themselves, where they're drawing those relationships themselves, all of those things.
It's coming back to what you said in the beginning of the show, the 4 M's. That's absolutely, and I think that is so necessary. What you said was, if the textbook doesn't do what you want to do with the learner, and doesn't explore at the depth you want to, there's a wealth of resources
Yes.
out there. There's a www that you can go to.
It
that
can
will
be
give you-
dangerous as well.
It can be,
Yes.
as we've seen. It can be.
I think there are many things you can use this in so many ways to emphasize other points within the maths classroom. The whole thing about building definitions, about modifying things. You're not absolutely correct in the beginning. You're going to build on that correctness. And there's always this mindset in maths that you have to get it right the first time.
Yeah.
And this is a nice way to show that they don't have to get it completely right. They need to be able to build on it, though.
Exactly, and upset the apple cart deliberately. Throw a pair in there and let them see that the pair doesn't belong.
Yes.
And also, when I said earlier, mix up the properties and work with only the properties without the shape. And can a figure that has opposite angles that are 90 degrees have sides that are not parallel, for instance? Ask that question and let them work with that.
Yes.
Because up to now, the opposite angles 90 degrees in their little frame or in their frame of reference is the square and the rectangle. Can I draw that figure?
Yes, of course.
They don't see this possibility. Often they don't see it, where you have a right angle. So they don't see that as a tool and this as another tool that you can use. And superimpose the two, cut away there, you've got a quadrilateral with opposite angles that are 90 degrees, but the sides aren't parallel. That's how you want them. They must be able to take the property and reason with the property to get back to the shape.
Now, do you know of any resources where they do these types of investigations that encourage the geometric habits of mind?
There's a lot of, and I'm not sure about the grade 10 curriculum. I think the construction that happens in the grade 10 level is actually drawing. It's not construction. But books that works by constructing shapes works that way.
Okay.
You work with a property, and from the property you go to the shape. You go back to the shape. So the idea of constructing two perpendiculars in such a way that the two right angles lie opposite each other, but the sides are not parallel.
Yes.
So that's deliberately not working with the issue of parallel.
Yeah. I think I'm going to look for some resources tomorrow morning and see if I can post some on the blog that lend themselves more to this than what we've currently got.
I think there's the website. I'm not sure, and I don't think if we can have time to quickly go there, Dylan. We don't have time.
Yeah.
It's www.learner.org if teachers go there. I think it's that website where they actually work with constructions, and they actually work with the relationships to construct. So and there's quite a few illustrations on there. Oh gosh, okay, I don't know where you go and look for there now. But yeah.
Well, there's the website. I will find where to look, and I'll post it on the blog.
Sure.
Jacques, it's been fantastic having you. You've gone through quite a lot in the space of an hour, and it's been fascinating. It really has. Thank you for coming.
Thanks for asking me, Helen. It's been wonderful having this discussion.
We hope to have you back again soon. And thank you to Dylan for all of your input and for all the clicking. And we will see you again next week when we talk about grade 11 content. Thank you very much for joining us. Bye.